Yes, it's recording. All right. So today we are very happy to have Professor Harley Katz with us. He is presenting his work and talking about a new generation of galaxy formation models, and he's going to show us what we can expect from CGM. Harley is an expert in galaxy simulations. He has worked on various different fields, including reionization, Lyman continuum leakage, and stuff like that. But in particular, today he's talking about non-equilibrium chemistry, which has significant consequences for circumgalactic medium, diffuse gas around galaxies, and all the cool stuff that we are interested in. Harley got his undergraduate degree from University of Maryland, College Park, and then he went on to do his PhD from University of Cambridge. And now he has joined the faculty of University of Chicago. So without wasting more time, here I will let Harley show us the exciting stuff that he is working on and amaze us. So Harley. Yeah.
You set the bar high. I don't know if it'll be amazement, but hopefully it'll be somewhat educational. But yeah, thanks to Xiaowen and Sanj for organizing this. It's great to be here with you guys. As Sanj said, I'm primarily a theorist. I work at University of Chicago, mainly on galaxy formation simulations, but I'll do my best to connect these things to observations as well throughout this talk. So first off, it only occurred to me this morning that today is Halloween. So this is my best ChatGPT effort of when I plugged in CGM and Halloween. This is what came up. And I realized for those of you on the East Coast, I'm between you and mounds of sweets tonight. So we'll make sure to keep this sort of on time. Okay, into the science. I think now, as it almost always is an extremely exciting time to be studying diffuse gas, and in particular the CGM. I've primarily been thinking about it in the context of emission. This is also true in absorption. And here's just 3 examples that I think are really just astounding. The left-hand side is a map from the Duvet survey of an edge-on galaxy where they can use the direct method metallicity.
Can you hear me?
Yes, I can hear you.
I cannot see your screen. Are you sharing?
Yeah. Did it stop?
I think so.
I can see it. I can
working
see
here.
it.
I see it.
You see
I can see it as well.
Working for me.
Okay, sorry.
Give me 1 second. Share. Can you see it now?
Yes, I can see it now. I don't know what happened before.
Okay. If you can't see it again, just let me know. So anyway, I'm particularly excited about a lot of the CGM observations and diffuse gas observations that are coming out in an emission. So the left-hand side is an example from the Duvet survey where what you can see is we can use the direct method metallicity above and below this galactic disk, and you can see this really strong metallicity gradient both in the vertical and horizontal direction. And I'll come back to this one in a little bit. The middle one is from Muse. It's really amazing. You're seeing Lyman alpha emitted by the cosmic web, and you can really see this, large scale filament of order kiloparsecs. And this is from a couple years ago. And then very recently, what you're looking at is more of a serendipitous discovery of oxygen-3 in emission around a massive high redshift galaxy. And so the fact that we're detecting this gas directly, I think, is really fantastic. Now, of course, modeling it is extremely difficult. And I think there's been a lot of progress made recently. And the methods, I would say, are really maturing for extracting the physical characteristics of CGM and diffuse gas. I'm just gonna highlight 2 examples of this. So there's a recent paper by Cameron Hubbles and Kate Rubin, where they have this really cool model called CloudFX, where you can sort of vary these parameters smoothly and really try to extract the properties of the CGM in sort of a really clever parametric way. And then sort of from the side of emission and absorption, we've recently created with Thibaut Garel in Switzerland a public grid of 20,000 simulated spectra of Lyman alpha, magnesium-2, silicon-2. And you can really run parameter inference when these public grids are getting as large as they are. And these methods are really great. They're sort of no longer glossing over some of the small scale properties of the CGM. But what these methods do is they often tell us the sort of what. They tell us what are the physical characteristics of the CGM, but they don't often tell us the why the CGM looks the way it does. And so For this region, the CGM is extremely complex, and numerical simulations can be an invaluable tool. You're not going to run parameter inference with numerical simulations, but because you're modeling the CGM from first principles, you can try to understand why it looks the way it does. That being said, simulating the CGM remains a very, very strong technical challenge. And so on the left-hand side, this is my best representation of the galaxy. You have a sort of disk in the center. You have radiation coming out of the disk that's sort of hitting an outflow in pre-existing CGM clouds. You have some background radiation field coming from the galaxies in AGN nearby. And sort of you have to encapsulate all of this. And I'm gonna highlight 4 of the many reasons why simulating the CGM remains difficult. The first one is a rather technical point, and is that most simulations, the resolution tends to follow mass and not volume. And this is very much the case in what we call SPH simulations, but it's often the case in grid codes too. And so even though the galaxy might be very, very highly resolved, it's often the case that the CGM and the diffuse gas, there may be a resolution issue. The second is, as you can see here, the CGM is exposed to both the local radiation field coming out of the galaxy and the UV background. And in most of our simulations, we don't actually propagate the radiation field coming from the stars or the black hole in the system. But to actually do this properly, you require radiation transport, which is incredibly expensive. A third reason is that the density of the CGM is low. And for this reason, equilibrium timescales may be wrong. And so, for example, if you're using tools like Cloudy or a photoionization code to model the diffuse gas, if the gas is not in equilibrium, these codes almost always assume equilibrium by default, in which case they might not be the most ideal tool. And finally, the last point is that many of the sort of lines that we're interested in, for example, Lyman alpha or magnesium 2, these transitions are resonant. And that means the photons have to diffuse both spatially and in frequency. And so to model that properly, you need something like Monte Carlo radiative transfer and post-processing. And this is, of course, doable. It's just expensive. Okay. And I think there's sort of been a renaissance in simulations recently, and a huge amount of the effort has been focused on the resolution issue. And so this was pioneered by people like Cameron Hummels, Molly Peebles, Josh Suresh, and here's just a few examples where people are using grid codes or semi-Eulerian base codes. And what they do is they just, they take their simulation and they just enforce that in the diffuse gas, they just add more and more and more resolution elements. And so what you can see here, here's an example from the Tempest suite. On the left-hand side is just, the galaxy in a typical simulation where resolution follows mass. And as soon as you enforce that the resolution is much higher, you can see that there's just more H1. The same thing holds in Foggy. On the left-hand side is the normal simulation. The right-hand side is where they've enhanced the resolution artificially. Same thing goes for simulations by Freka Vandervoort. Here's a more recent one called Gibble, and then one from Martin Ray from our own group. Okay, and you can ask, what have we learned from these simulations with enhanced resolution? And there's quite a bit, but I'm going to show 3 particular examples. The first one is that the number of neutral absorbers increases, but I would argue that the exact details of this remain a little bit uncertain. So on the left-hand side, what you're looking at is on the x-axis is H1 column density, and on the y-axis is the covering fraction of this neutral gas. And what you can see is that this blue line represents their sort of simulation where the resolution elements follow mass, and they seem to be struggling to predict the location of these cos halos data points. But as soon as they add more and more resolution, the number or the covering fraction of these low column density absorbers is going up, and such that, when they go to 1 kiloparsec spatial resolution, all of a sudden the simulations seem to agree. So not changing any of the physics, just resolution. And on the right-hand side, you can see the same result from the Foggy simulation. So this is from Molly Peebles, where on the x-axis is, again, H1 column density, and the y-axis is sort of the fraction of sight lines with greater than this column. And indeed, the standard refinement and the sort of hyper refinement in orange, there's a clear difference. Now, as you can see, that the difference is stronger in Freka's simulations than it is in the Foggy simulations. And so we haven't quite converged on how strong this effect is, but it's clear that as we go to higher resolution, we're getting more of this neutral gas. Another thing that we've learned is that convergence in the CGM is extremely difficult. And so here's a result from the Gibble suite of simulations. On the x-axis is cloud mass, and on the y-axis is just counting the number of clouds with that mass. And each of these different color lines represents sort of different refinement levels. So this yellow line here, that has the worst resolution. This red line has the intermediate resolution, and this gray line has the best resolution in the simulation. And as you can see, as you go to higher and higher resolution, the number of massive clouds seems to be relatively well converged, but you're missing all of the small scale structure in the low resolution simulations. And it's actually not clear where this stops. You know, these simulations don't fully have MHD, thermal conduction, turbulence, cosmic rays. And in order to actually get this cutoff correct, all of these processes need to be modeled simultaneously. But for now, convergence remains an issue for almost all simulations. Another thing which I find particularly interesting is that when we enhance the resolution, we see slightly different effects of feedback. So on the x-axis, what you're looking at is just, we're indicating simulations with a typical resolution where it follows mass, or where we enforce that the CGM and outflows get more and more highly refined moving to the right. And so on the y-axis, it's either the metal loading factors, the energy loading, or the mass loading. And if you look close to the disk, the resolution doesn't really impact this because it was already resolved pretty well anyway. But if you look far away from the disk, what we find is that as we increase the resolution, the mass loading, the energy loading, and the metal loading also go up. Again, not changing the physics, just changing how well the CGM is resolved. Okay. Moving on to radiation transport, this is also becoming commonplace. There's now algorithms where we can solve radiative transport reasonably efficiently, although it's still absent from most large-scale simulations. So this is a result I like to highlight from the gasoline group, where on the left-hand side, they ran a simulation with a uniform UV background. And on the right-hand side, it's the same simulation where they propagated the UV background. So no local radiation, just propagating the radiation from large-scale sources. And what you see is that there's way more neutral gas in the right-hand side because self-shielding is just encapsulated in a much different way, which leads to much more neutral gas. Okay. Local radiation also seems to be important in both the context of AGN and star-forming galaxies. So on the left-hand side, you're seeing a plot from one of Ben Oppenheimer's simulations where what he did is he put a black hole in the simulation and just turned on and off the radiation from the black hole. Now, the radiation wasn't propagated, but it was sort of modeled in a sort of optically thin limit. And what you see is that when the sort of AGN is spiking or going down, you get deficits in H1 or spikes in oxygen 6, okay? And so it's clear that the oxygen 6 and H1 are very much dictated by the local radiation field. On the right-hand side is another example of this from a recent simulations by Zhu and Springle, where if you look at oxygen 6 and magnesium 2, the left-hand columns are density versus temperature, and the regions highlighted are where you find the oxygen 6 in a typical simulation. And on the right-hand side, what you see is the oxygen 6 once the radiation, once again, in a more simplistic fashion, is included, and there's a very clear difference. And the same goes for magnesium 2. Something that I tend to work on is very high redshift, and we know that the local radiation is extremely important for pressure smoothing the diffuse gas in the ISM. So on the left-hand side is a simulation where you're looking at the gas distribution in the case where there's no radiation. The center is the dark matter distribution, and you can see without radiation, the gas pretty much follows dark matter because of, it's just attracted by gravity. However, as soon as we turn on the radiation transport, we've completely pressure smoothed the intergalactic medium and the cosmic filaments. And what happens is you see that the gas distribution is much more puffy, and that all of these small scale filaments that you see in the dark matter are no longer present in the gas distribution. Okay. And that's, these are nice images, but this has really serious effects for galaxy formation, in particular for dwarf galaxies, because if you look at the baryon density on the y-axis in the simulation with radiation to the simulation without radiation, on the x-axis, you're looking at the distance from the center of these cosmic filaments. And what you can see is that inside these cosmic filaments, as we go from very high redshift here on the right to low redshift here on the left, as reionization is taking hold and the radiation is propagating over these filaments, the baryon densities are dropping by around 80%, 70% to 80% inside these filaments. And what this does is it quenches these dwarf galaxies and even more massive galaxies by starvation. So it's really clear that this radiation is important. Finally, non-equilibrium effects are often included now in simulations for hydrogen and helium, but not for metals and molecules. And I'd argue that this is really important. And the reason why is because, if you take a typical recombination rate of sort of 10 to the minus 12 centimeters cubed per second and a relatively low electron density of 10 to the minus 3, the recombination timescale is of order 30 million years. And this number can sort of go up or down depending on temperature, density, ionization state, et cetera. But it's a significantly long time scale. It can be longer than the sort of star formation time scale in your galaxy. And so here I just want to highlight, some work by Alex Richings where they looked at the mass in molecular hydrogen as a function of velocity. So this is sort of the outflowing molecular gas. And the simulations in the solid lines are run with full non-equilibrium chemistry, and the simulations in dotted lines are the equilibrium approximation. And what you find is that as soon as you go to non-equilibrium, they tend to get more molecular hydrogen in these fast-moving outflows. And if you look on the right, sort of something similar can be found for carbon-2 and carbon monoxide. Finally, when it comes to Monte Carlo radiative transport, there's now numerous public codes that can compute resonant line RT. Here I'm just highlighting 3 examples. On the left-hand side is an image of Lyman alpha emission from an isolated disk galaxy, which is run using the Colt code, which is by Aaron Smith. This middle panel shows you the full cosmic web in Lyman alpha from the TNG simulations computed by Chris Birol. And on the right-hand side, what you're looking at is the magnesium-2 maps computed with our code called ROSCAS for a magnesium-2 emitter, absorber, and one with a P Cygni profile. So this resonant line RT is becoming more common. It's just very expensive. So the key takeaways I want you to have from this introduction is that, computing the CGM from first principles in a galaxy formation is very difficult. That being said, most of the elements we need to do it, and especially compare with observations, are actually now possible, but connecting them in a single simulation at the resolutions required is still extremely difficult and extremely expensive. So we're not quite there yet. We're still missing some of the physical processes, such as, thermal conduction, cosmic rays, et cetera, but there really is an extreme amount of progress. And so for the sort of next 30 minutes or so, what I'm going to be talking to you about is sort of our efforts to try to improve things from the modeling side. So over the last 2 or 3 years, I've been developing a brand new code, and it's called Ramses RTZ. And a single sentence, what it is it's non-equilibrium chemistry coupled to on-the-fly radiative transfer. So what we do is we try to take all of the properties that control things like ion abundances, molecular abundances, and dust properties. And these are things like collisional ionization, photoionization, cosmic ray ionization, as well as, recombination processes, whether or not they're radiative, dielectronic, or recombination on dust, as well as, the different chemical reactions such as charge exchange and dust formation and destruction. And what we do is we couple them to the on-the-fly radiative transport in the simulation where the radiation is coming from sort of stars and black holes. And to sort of emphasize why this is important, on the x-axis, what I have is time in megayears, and on the y-axis is the ionization fraction for things like oxygen, nitrogen, carbon, magnesium. And what we do is we just start the simulation where everything is in neutral state. So it's fully, for example, in oxygen 1. And if you just let this evolve in time, it moves to some equilibrium abundance, which is given by these dotted lines. And so these dotted lines are sort of the equilibrium abundances you would predict with a code like Cloudy for whatever the physical situation this is, okay? And so the point is Cloudy almost always gives you these dotted lines, but in the real CGM, you can be anywhere along these curves, okay? And so that's sort of the non-equilibrium aspect of these simulations. And so you can ask, why have people not done this before? And sort of the answer is that they have, it's just extremely slow. And so the next thing that we did is, in addition to just getting the ionization states and the dust properties and the molecular abundances correct, you also have to get the thermochemistry and the thermodynamics of your gas correct as well. So we've also included processes such as cosmic rays, photoheating, photoelectric heating, heating from H2 formation and destruction, heating from dust, as well as various cooling channels from, primordial to carbon monoxide, dust gas reactions, as well as all of the different channels, for example, adiabatic expansion, shocks, supernova turbulence that you get in a galaxy formation simulation that you won't get in a post-processing code like mappings or Cloudy. And of course, we have to calibrate this on something. And what we do is we try to calibrate this to the Milky Way's interstellar medium. So on the x-axis, you're looking at density, and the y-axis is temperature. And sort of these red curves and these orange dotted points, what these are sort of our best estimate for what the Milky Way's interstellar medium looks like. And so our green line, this one here, which represents solar metallicity, this one has been calibrated to try to reproduce the conditions of the local interstellar medium. And then these different color lines show you how temperature and density are related when we sort of evolve this to different metallicities. And you can do the same thing with gas pressure. And sort of the key innovation that we made when we did this is we developed essentially a new semi-implicit ODE solver that's about 15 times faster than typically used solvers in the field. So now we're sort of at a place where the computers are good enough where we can run all this physics simultaneously on the fly in the simulation. Okay. And so I realize for many of you that sort of don't think about these microphysics very often, that's really abstract, but to sort of put this into perspective, while a typical simulation is going to predict things like intrinsic galaxy properties, so here you look at, the gas column density, the stellar distribution, or the temperature map in a simulation, when you combine Ramsey's RTZ and PRISM, we see much more, okay? So we have, the ionization states of hydrogen. Here you can see it face on or edge on in an isolated galaxy simulation. You, of course, get the temperature map. We have, molecules like molecular hydrogen, carbon monoxide, low ionization states like O1 and C2. We have the full radiation field from the, the far UV, the infrared, all the way up to the helium-2 ionizing bands. And you can see that they are indeed very different. Pretty much any ion that you could want. And one of the really nice things is because we can solve for the level populations on the fly in the simulation, we can predict the emission lines in the simulation from first principles. So these are no longer post-processed. This is actually a direct prediction from the simulation, and probably one of the reasons I've been so excited about all of these new observations of the CGM and emission recently. Okay. Now, I want to emphasize for some of the skeptics out there that Ramsey's RTZ has been very, very heavily benchmarked against cloudy. And the idea is that if you sort of set up a cloudy model and try to set up a very similar model in Ramsey's RTZ, you'll ideally get a solution that's very close to one another. And here's just an example of this. On the x-axis is gas density, and on the y-axis is line luminosity. And what we did is we just put a single source at the center of a cloud and just in pure spherical symmetry, evolved it to equilibrium and calculated what the line luminosities are of, our favorite strong lines, whether it's oxygen 35007, the O2 doublet, H alpha, H beta, et cetera. And I actually forget which one of these is R lines and which one of these is cloudy, but as you can see, they pretty much agree extremely well. Now, for those of you with a keen eye, you'll notice there are some subtle differences. There's a little bit of a difference between, our models and cloudy and the oxygen emission lines. And this is just because the temperature is very slightly different in the highly ionized region. And finally, we, assume a different dust depletion rate for nitrogen. So, Ramsey's RTZ is not cloudy. It's a very different code, but in very similar setups, they give, extremely similar answers. Now, one of the really nice things about this code is we can move beyond these spherical symmetric equilibrium models. And this is just one of the examples I'm really particularly excited about. This is, an interstellar medium simulation, not circumgalactic medium, but I hope you're excited about it as well. Instead of assuming spherical symmetry, what we can do is, the ISM is turbulent. We can just put, the same source in a turbulent box. So here you're looking at a gas density map, a column density map, and you can see, it's no longer a homogeneous gas distribution. And if I plug a source right at the center, you create sort of a Stromgen region, which is no longer a sphere. It has this very peculiar butterfly structure. And if you look at, the oxygen 2 map integrated down the line of sight, or just, a slice, you see that the oxygen 2 forms right at the edge of your Stromgen region, whereas the oxygen 3 is more volume filling. And what you can do is you can just calculate the emission line luminosities coming from these turbulent Stromgen regions compared to the same median density in a spherically symmetric region. And if you do that as a function of metallicity on the x-axis, if you look at, for example, the O3 over H beta ratios, the stars are what you'd get assuming spherical symmetry. And these sort of cyan points with error bars are just the averages over 10 realizations of a turbulent medium. And there are clear systematic effects. You can see that O3 over H beta goes down, N2 over H alpha goes up, and O32 goes down. So if you're using these diagnostics to interpret whether it be the ISM or CGM, it's clear that turbulence matters. Okay, and I think that's extremely exciting. And what's really nice is some of these results, are consistent with many others in the literature. Okay, that's all well and good, but I want to move now to more galaxy formation simulations. And here's just one example where we're running Ramsey's RTZ now in a full isolated galaxy. And the experiment we tried to do is we wanted to know, given our isolated galaxy, can we infer the mass outflow rate from the simulation, based on mock observations? And so if you want to measure an outflow rate, one of the great ways to do it is you can sort of look down the barrel. So the idea here is your galaxy is face on and you're sort of staring right down through the outflow. And if you assume that the outflow is very smooth and collimated, you can write down this equation for the mass outflow rate. It goes as, 1 solar mass per year times the outflow covering fraction, the column density of the outflow, the area subtended by the outflow, the velocity of the outflow, and it's inversely proportional to sort of the vertical extent of the outflow, okay? So as the covering fraction, column density, and area and velocity go up, you have a higher mass outflow rate. And if the outflow is more sort of extended, then the outflow rate is actually lower. And it turns out that almost all of these parameters you can estimate if you can view a galaxy down the barrel. So the idea here is I have my disk with some outflow rate, in front and behind it, and my telescope is staring through this outflow onto the disk galaxy, okay? And so to give you an idea about where these parameters come from, if the outflow is launched by supernova feedback, the radius tells us something about the area of the outflow. Unfortunately, if you're down the barrel, the outflow extent is, unknown as is viewed in projection, but, these are sort of order 1 uncertainties. If you look at the spectra and take a spectra of this, the light that's coming out of this galaxy through the outflow, what you find is that there tends to be an absorption feature which is shifted from line center. So line center is given by this vertical dotted line, and you see the absorption feature is now blue shifted. And sort of the delta lambda here tells you something about the velocity of the outflow. And the depth of this absorption tells us something about sort of the optical depth and covering fraction. Okay, so besides the vertical extent of the outflow, we can sort of infer all of these different properties, and we can differentiate between optical depth and covering fraction if we have a doublet like what I'm showing you here, which is the magnesium-2 line. So we did simulate this. Here I'm showing you a magnesium-2 column density map in our simulation. It's an isolated galaxy simulation, so you see the outflow is protruding vertically, above and below the disk. And what we can do is, since it's a simulation, we can, view the galaxy from any angle that we want. And so here I'm just showing you what the spectra of magnesium-2 look like, sort of as we sort of circle from top all the way down to looking from the galaxy underneath. So when you're viewing the galaxy from the top, that's this red spectrum up here, you see this beautiful P Cygni profile where the absorption is indeed, blue shifted from line center. As you go perfectly edge on, that's this gray line here. The velocities are all tangential and not along the line of sight, which means that all of your absorption is now happening on line center. And then finally, as you go now underneath the galaxy and viewing it down the barrel from the bottom side, again, we recover our P Cygni profile where the absorption is again blue shifted. So what we can do is we can pretend we're an observer and we can fit these P Cygni profiles and try to figure out what the outflow rate is. And that's what you're seeing here. So on the x-axis is time in the simulation, and on the y-axis is the outflow rate, either viewed from the front side of the galaxy, so that's on the top, or the back side of the galaxy on the bottom. Now, of course, there's a little bit of a dependence on where we measure the outflow rate in the simulations, but if I just take 3 fiducial radii, 1 kiloparsec, 2 kiloparsecs, and 3 kiloparsecs, they're a little bit different, but they're roughly similar, okay? And there is a difference between the front and back side. But if I sort of fit this pure partial covering model and sort of fit these P Cygni profiles, what I find is this black line. And in general, what we seem to find is that if you try to extract the properties of the outflow from the spectrum and compare it to the true underlying value in the simulation, in general, we find that the measured values underpredict the true outflow rates. And sort of we dug into understanding why this is the case. And there's actually many reasons, but at least in our simulations, one of the strongest culprits is what we call density inhomogeneities. And the problem is basically this, right? If we assume that the outflow is smooth and collimated, what we're trying to do is sort of measure a mean column density in the outflow and then convert that into a mass outflow rate. But if I do a very, very simple experiment where I just assume that my outflow is 1,000 different parcels, okay? And so on the x-axis, I'm plotting some parameter which I call inhomogeneity, which tells me how much the density fluctuates between those 1,000 different parcels. And if I start at 0, where this outflow is perfectly homogeneous, and I measure what we call the discrepancy, which is the difference between the true and predicted value of our mass outflow rate, you find when the outflow is perfectly homogeneous, there is no discrepancy, okay? You get the exact right answer. However, as I make the outflow more and more inhomogeneous, you find that this discrepancy keeps going up and up and up. And essentially, it's all linked to this inequality. And it's basically, if you have flux going through, regions of different optical depth, unfortunately, the amount of flux you get from this is not the same as what you get from sort of the same gas that has the same mean tau, okay? And so this bias is such that you always underpredict the mass outflow rate. Now, it's not all bad, okay? What we can do in the simulations is we can measure the distribution functions of column densities in our simulation. And so here on the x-axis is the column density of magnesium-2. And this is sort of the number of pixels inside my outflow rate aperture. that have a column density greater than this value given on the x-axis. It's actually the inverse of it, okay? And so if this was a delta function or sort of a step function, what you'd find is that the outflow is perfectly homogeneous and every gas parcel has the same column density, but clearly it's not. There's, you know, a real spread out distribution here. And what we've done is we've parameterized this distribution with some function. And if we just modify our outflow rate measurement by accounting for the fact that there is a distribution in gas density, and we plug that back in, the dotted lines were sort of our original estimate, assuming that everything was perfectly homogeneous. And now the new black solid line is the estimate allowing for this distribution function that's parameterized based on the simulation. And of course, there's a lot of scatter and it's not perfect, but it's clearly doing much better. And I think that's great because if we can get IFU measurements in the future, which are measuring these column densities on sort of smaller scales, we can parameterize this distribution function and then once and for all solve this problem. Another cool example, this is once again results from Alex Cameron from the Duvet survey. And what they did is they measured this line, this oxygen 34363 emission line in the outflow of one of these edge-on galaxies. And by measuring this line, what they can do is they can estimate the metallicity in principle in a very accurate way. And so what you can see is that there tends to be low metallicity sort of on the left side and right side of this disk, but sort of above and below the disk, the metallicity tends to be a little bit enhanced. And sort of the picture that Alex came up with was you sort of have, you know, metal poor inflows here along the disk, and then this metal enriched outflow, which they can measure with this oxygen 34363 line. Okay. So what Alex did is Alex took one of our simulations. This is now an isolated galaxy simulation. You can see there's, you know, outflows above and below this disk. And what you're looking at is the oxygen 34363 emission map of the simulation. So you can see there's plenty of this oxygen 34363 line above and below the disk. And what he did is he used this line in combination with the 5007 line and H beta line to infer the metallicity in the same way he did with his galaxy from Duvet. And so on the x-axis is the true metallicity in the simulation, and on the y-axis is the measured metallicity in the simulation. And so this dashed black line is the one-to-one relation, and all of these individual points are Alex's measurements. And what you can find is that, again, systematically, there tends to be about a 0.3 to 0.4 dex offset between the metallicity that we're actually measuring and the true metallicity in the simulation. So Alex was very curious as to, you know, why is the metallicity underestimated? And so the first idea that he had was maybe it was ionization corrections. And what this comes from is when we look at these emission lines, we tend to see O2 and O3, but what if, for example, all of the oxygen is not in those two particular ionization states? And so that's the first thing he checked is the difference between the true oxygen to hydrogen and just the oxygen that's an O+ or an O2+. And so on the x-axis here is metallicity, and the y-axis is the difference between the measured and the true value. So what Alex did is he just calculated the metallicity of O+ and O2+ and versus just the total metallicity. And what you find is that sort of the typical values are given by these horizontal orange and purple lines. And even if he, you know, corrected for this ionization, the true value would, you know, fall up at the 0 line. There's still a very strong discrepancy, even correcting for this ionization. And so this ionization can give you about 0.1 dex. That's the difference between sort of, you know, this dot and this dot are up here and up here. Sometimes it's a little bit smaller, but in general, ionization corrections matter, but they're not the root of this problem. As it turns out, it's almost very similar to what we saw for the mass outflow rates. And so if we write our metallicity oxygen to hydrogen, which is, you know, O+ over H+ plus O2+ over H+, you can reformulate this, you know, metallicity as a ratio of luminosities between oxygen 2 and H beta, oxygen 3 and H beta, as well as the emissivities of H beta and the O2 lines and the emissivities of H beta and the O3 lines. And the problem arises because the H beta line emissivity, shown here as the black curve as a function of temperature, you know, drops as a power law, whereas the O3 5007 line and the 4363 line are increasing exponentially with temperature. And so what this means is that you're sort of more sensitive to the brighter regions of O3. And because the O3 emissivity comes in at the bottom, when you overestimate the emissivity, you tend to underestimate the metallicity. So in the case where all of your temperature, sort of all of your gas was at the exact same temperature, you'd get a perfect metallicity. But as soon as there's a distribution, you tend to bias yourself to the sort of brighter, hotter regions of the diffuse gas. And so Alex went and actually measured the temperature distributions of the O3 and O2 emitting gas. And that's what you can see here. It's a probability distribution function of the temperatures of the, the oxygen 2 and oxygen 3 just in this box, which is, the outflow above the disk. And you can see this extremely long tail, especially for the oxygen 3, which is what's biasing our results. Okay. And so we can fix this problem again by trying to measure these temperature fluctuations either directly, for example, using something like, a very fine-grained IFU, or if you trust our simulations, you can try to calibrate based on the distributions that we see in the models. So these are, those are all well and good, but those simulations were all isolated, which are, really ideal laboratories for these simple experiments. But of course, galaxies are in cosmological environments, and the CGM is sort of a mixture of inflows and outflows. It's not just an isolated disk. So now what we're doing is we're moving beyond those simulations of isolated disk galaxies into a fully cosmological environment. So this is a new simulation that we call Megatron. And what it is it's an early forming Milky Way mass galaxy. It has extremely high resolution. The stellar resolution is 500 solar masses. We model individual POP3 stars, and at the time they form, the spatial resolution is around 1 parsec. We sample the IMF stochastically from some initial mass function. We follow all of these different feedback processes: core collapse supernova, 1A, hypernova, parent stability supernova, stellar winds. And these feedback processes were all validated on similar Milky Way mass galaxies at redshift 0. We have the full, 82 species chemistry coupled to 8-bin radiation transport. And as I'll show you in a second, we enhance the resolution in the CGM, similar to many of these other projects that you've been looking at. And we have various sort of modifications of what we call our fiducial model. And so here I'm just showing you sort of a map of a single galaxy at redshift 4. It's, a beautiful spiral galaxy. If you can, zoom in really close, you'll see the H1 here. You see there's a molecular hydrogen and CO disk. And these are, just a subset of the different physical properties we get from the simulation. But you see how carbon 4 looks super different from carbon 3. There's nitrogen 1, nitrogen 2, all the way down to, various iron species. And so we get this at every single snapshot and every viewing angle you can imagine. And I'll zoom in on one of the really interesting ones, which is just, the oxygen species. So this is, viewed, down the barrel again. So we see our oxygen 1 disk. You see that a lot of the CGM around this galaxy is in the sort of lower ionization state neutral phase. And as you go to higher and higher ionization states of oxygen, you see that the sort of, O4 and O6 are wrapping around these weird filamentary structures that are showing up in the low ionization states. And which I think is, really cool that we're resolving. Is there a question? No? Okay. I think it's really fantastic that, this is done fully in non-equilibrium now on the fly, connected to local radiation transport. And so the simulation is a little bit unique. We've engineered this galaxy. We say we genetically engineered this galaxy to be an early forming Milky Way mass galaxy. And so what I mean by that is on the x-axis is redshift, and on the y-axis is the virial mass of the halo. So what we did is we started with an initial condition, which is given by this red line, and the shaded regions shows you the sort of formation history distribution of similar Milky Way mass galaxies in the illustrious TNG simulation. So this galaxy was already, a 2 sigma outlier in the fact that it forms really, really early with respect to, a typical Milky Way mass galaxy. And we've modified the initial conditions in a very systematic way so that the mass history now looks like this, where it's now, at least a 3 sigma outlier, and it almost becomes Milky Way mass by sort of redshift 4 or so. And what I want to do is I want to highlight sort of this region here between redshift 5 and 4, where loads of these sort of roughly equal mass progenitors are colliding to form this one Milky Way mass galaxy. And so here's a movie. So we have dark matter, gas, stars, gas temperature, and then the Lyman-Warner flux and the ionizing flux. And what you can see is that the ionizing flux is pulsating. You see these sort of waves, which are consistent with the star formation history of the galaxy. So as the star formation goes up, it produces loads of Lyman continuum photons, and those get pumped out into the circumgalactic medium, and they propagate to larger and larger distances or get absorbed. And as you just saw, there was a massive starburst, which created this, huge wave of Lyman continuum photons. And for many of you, you've probably seen simulations exactly like this. Almost all simulations with radiated transport, will get you all of these, different physical properties. But what I suspect you haven't seen before is a movie like this, where what you're looking at now is the emission maps of H alpha, oxygen 3, the 4363 line, the O2, the nitrogen 2, and the helium 21640. And those waves of ionizing radiation, if you just focus on the top right panel, that's, ionizing and pushing us into this ionization state of oxygen 3, which is allowing it to sort of emit. The same thing happens in H alpha, and you can see that the CGM is fluorescing in emission as these waves of Lyman continuum photons sort of pass by the CGM gas. Okay, so this is a very particular point in the simulation. I want to show you the sort of full movie now. So this is starting at very high redshift. So early on, we have population 3 stars, so no metals. You start seeing H alpha in emission in this top left. Okay, and so these galaxies, these very early galaxies are pumping out Lyman continuum photons into the intergalactic medium. But at this time, there is no well-formed galaxy, okay? It's, a disparate, patch of just a bunch of small dwarf galaxies. And as more and more Lyman continuum photons are produced, those Lyman continuum photons escape the galaxy and they start reionizing the IgM. So you can now see the cosmic web start lighting up in H alpha emission. And in the meantime, you start seeing metals. You can see the oxygen 3 light up now. The metals are being pumped out by these first generations of stars. And so as these waves of Lyman continuum photons roll over these filaments, they illuminate and then they recombine again as they're fluorescing in emission. Okay, so I'm going to let this run a little bit longer. Eventually, you'll start seeing nitrogen get produced. So this is more produced in our stellar winds than it is in the core collapse supernova, which is why there's a significant delay. But now you'll start to see it appear in the bottom left. And as we get to about redshift 7, this sort of patch around this Milky Way mass galaxy is almost fully reionized. And now you really see the cosmic web has lit up. As the supernova feedback gets stronger and stronger, you can actually collisionally excite the helium-2, such that you see the helium-2 in emission in the cosmic web as well. And then eventually this thing is going to start to merge, and you'll start seeing the oxygen and nitrogen really, really light up as the metals are produced. And so now we're about redshift 6. The sort of local volume is fully ionized, which is why these filaments sort of remain bright. And you can start seeing these mergers now, which are going to elucidate a very strong stall formation rate, which will produce heaps of metals. Okay. And so for the interest of time, I'm going to move a little bit forward. But I also want to highlight one of the key things we're showing in these simulations is that instead of just refining on all the diffuse gas, we put extra resolution elements where the cooling length is unresolved in our simulation. So on the left-hand side, what you're looking at is a map of the grid level in our simulation. So this cyan is very highly refined and this brown has much lower level of refinement. Okay, and so this is the typical simulation where the resolution follows mass, and all of our grids tend to be in the interstellar medium. But on the right-hand side is what we do in our simulation, where we add extra resolution elements to try to resolve the cooling length better. And all of a sudden, you see these filaments pop up. These filamentary features are really where this extra resolution elements are going. So in the last couple minutes or so, I want to highlight sort of 2 key questions and 2 key results that we're learning from these Megatron simulations. And so the first one is, does the local radiation field matter and by how much? And the second one is the CGM out of equilibrium sort of in general, as well as with respect to the UV background? And so this is one that I'm really particularly excited about. So on the left-hand side, you're looking at just a hydrogen column density map of the galaxy around redshift 4, and it's this beautiful spiral galaxy, and you're viewing the disk edge on. Okay, so you see this sort of nice thin disk. The scale of this image is about 60 kiloparsecs. And on the right-hand side, what you're looking at is a map where the different color tells us the ratio between the photoionization rate coming from the radiation transfer solver. So this is the propagated radiation in the simulation coming from the stars inside this galaxy, divided by the photoionization rate of a UV background. In this case, it's a Hartmann-Dow UV background. And what you can see is that sort of in this cone above and below the disk, it's very green, which means that the local radiation field is completely dominating over the UV background, in some cases by more than a factor of 10. And on sort of the edges of this galaxy, where the radiation is shielded by the higher column density disk, you find that it's fully dominated in cases more than a factor of 10 by the UV background. So above the disk in this sort of wedge, you find local radiation field matters. And on the sides of the disk in this wedge, you find that the UV background matters. And I think this is really interesting. This is just a different snapshot now. You see the same ionization cone. I've tried to highlight that with these X's. If you look at the oxygen 34363 emission, for example, the same emission line we were looking at for metallicity, you can see that the vast majority of the emission coming from this galaxy is coming from this ionization cone. So it's somehow excited by the local radiation field and not the UV background. And what we've found is that these emission lines can have extremely different morphologies. So of course, O34363 comes from that ionization cone. The H alpha tends to come from, these filaments that are feeding the galaxy. So it's all over the place. It's not biased to the ionization cone. Nitrogen 2, a lot of it comes from the ionization cone, but it is sort of spread a little bit more sort of uniformly around the galaxy, while O34363 is a much stronger example where most of it is coming from the ionization cone. And orientation is clearly very important for this, right? So if you view the galaxy edge on, you can kind of separate what's coming from the UV background and what's coming from the ionization cone. And so here's the galaxy edge on. And so our ionization cone is sort of, you can see it in these wedges down here. But if you view it face on, now you get a much better depiction of where the filaments are coming to feed the galaxy. And so if we really want to sort of differentiate these two radiation fields, it's sort of important that we focus on galaxies that are edge on. And one of the reasons I think this is really particularly exciting is this is a result from Guo et al. 2023, where they looked at magnesium-2 in emission for stacks of galaxies viewed either edge on or face on. And what you can see is this color shows you the surface brightness. You see that most of the magnesium-2 is coming from this sort of ionization cone, the same effect that we were finding, whereas viewed edge on, it's sort of much more distributed around the galaxy, as we also showed for the H alpha emission. And finally, I'll just touch on the last thing, which is non-equilibrium effects. What we find is that in some cases, the ions are extremely out of equilibrium. So here we're looking at carbon-2. On the x-axis is gas density, and the y-axis is gas temperature. And the color map depicts where the ratio between the number density of carbon-2 in non-equilibrium to the number density of carbon-2 in equilibrium, okay? And it's mass weighted. So anywhere you see blue is where the non-equilibrium abundance of carbon-2 is in deficit, and anywhere you see red, the non-equilibrium abundance of carbon-2 is substantially enhanced. And in some cases, this is, by factors of 10 to the 4. So it can be extremely large when we're comparing sort of a simulation with RT to one with just an ordinary UV background. And so carbon-2 is a particularly interesting one because it spans between the ionized and neutral phases. Not all elements show this. Carbon-2, as I said, is a particularly extreme example, which is why I'm showing it. Nevertheless, it's still, to be determined how this changes, especially as a function of time and star formation rate in the galaxy. So unfortunately, the simulation is still in its infancy. It's still running at the moment, and we're still analyzing it. But I just want to highlight quickly what's coming. So we're going to look at a lot of things about the CGM and absorption, not just in emission. So we're going to look at things like covering fractions of various ions, how these are related to the physical state of the galaxy itself, quantitative measures of the non-equilibrium effects, as well as sort of performing the same exercises we performed on those isolated galaxies. Are we able to extract the physical properties of the CGM in a fully cosmological context? As you can see, I have this sort of affinity for the CGM and emission, and I think there's really interesting synergies with JWST, MUSE, and KCWI. We're going to look at things like, how gaseous filaments are feeding the galaxy and how cooling and non-equilibrium effects matter there. So with that, I just want to say I have one more slide after the conclusions, so don't get too excited. Ramsey's RTZ is a really great code for modeling the non-equilibrium chemistry, including metals and molecules, fully coupled to on-the-fly radiative transport. We've highlighted some of the biases with down the barrel outflow rates, as well as direct method metallicities. But I think there's an exciting opportunity to sort of fix these with better understandings of the fine-grained properties of the CGM. We've now ported everything into a cosmological context, and we've run this simulation called Megatron, which is a new simulation that reaches about a Milky Way mass at very high redshift. We refine on the cooling length, so we really put our computational effort in this diffuse gas. And there's sort of two interesting early results that I highlighted. We find this really cool ionization cone where the local radiation dominates over the UVB in different parts of the CGM. And it's clear that orientation does really matter, the structure of the emission that we see. And finally, some ions, in particular carbon-2, are extremely out of equilibrium, especially in the context of post-process models with a UV background. And we're aiming to do a public data release next summer, so stay tuned on that. And finally, I just want to say that, we're a very small team using Megatron and Ramsey's RTZ. And if you're interested in this data or you want to work with us, feel free to drop me an email, and we're sort of happy to share it and sort of help you out with your science goals. So thank you very much.
Thank you, Harley. This was very, very educational. We are amazed, and I see hands already. So let's start with the question. Is that Crystal?
It is.
Hi. So yeah, go ahead.
Thank you so much, Harley. That was just an amazing talk. I've learned a ton. I wanted to ask you about the spectacular ionization cones that you showed. And I'm curious, I mean, like the gas that's emitting in O3 and O2, are the ionization, is the local ionization field, right? Is that ionization front actually, you know, trapped in those clouds so that you would have case B recombination and, you know, an ionization bounded region, and any leakage is like, you know, through the picket fence? Or are some of those clouds actually like density bounded?
I'm going to try to sort of boil your question down. So you're asking if some of the clouds are like self-shielded inside the CGM, and you're sort of illuminating the layers of them. Perhaps.
Well, like, you know, when you say an ionization cone, right? You see the strong O3, you wonder if the ionization front has just, you know, plowed through the whole galaxy and that there's Lyman continuum leakage in that cone. But all attempts to measure and model Lyman continuum leakage seem to point toward, you know, picket fence models where the clouds you see emitting would look like they were ionization bounded, and the leakage is from channels between those clouds.
Okay, I think I see what you're saying. So this is, you know, extremely large scales. And so if I go back to this, you know, the galaxy disk is here, which is all where all the radiation is coming from, right? And so even so what's happening is, right, like this disk and this, like what I'll call the inner CGM, is not completely optically thin. And so there's a lot of absorption that happens in this inner region. So it's, as you can see here, the ionization cone is not particularly smooth. So you see, like right here, there's like this region that happens to be a little bit self-shielded. And then this wave is actually sort of a wave of star formation that's much brighter here than it is over here. And so we're still, you know, as we go to higher and higher resolution, this will just get more and more structured. And you see close to the disk, there is an extreme amount of structure there. Some of it is optically thin and some of it is optically thick. But I think the key effect is that when the radiation leaks out of this disk in the first place, it's almost always leaking vertically, or sort of out in this direction. It's never coming out sort of horizontal to the disk. So the reason why this ionization cone happens in this particular simulation is because we have this sort of really, really well-formed disk that has just crazy high column density along this direction. And so in a galaxy that, of course, doesn't have this morphology, you're less likely to get an ionization cone, or depending on how the Lyman continuum is leaking, if it's like through a channel, you might get like a narrow cone or something like that. But I think in this example, there's like a few channels where the radiation is coming out, which is producing this like sort of wedge that you see here. But indeed, it's clearly, it's not isotropic, right? So it's still very subject to what happens in the inner CGM. I hope that answered your question.
Yeah, thanks.
As a polite host, I'll restrain myself from asking too many questions. If you have other questions, please raise your hand or just speak up. If not, I do want to take the opportunity to ask a question. Well, maybe I'll restrain myself to only one question at this time. So one of the constraint we have as observers is kinematics. So as you showed in simulations, as you have higher resolution, you see more structure. That's the same for observers. When we do observations at higher spectral resolution, we do see more structure. So I guess it's the reverse problem. Now, I was wondering, you had all these different maps of different ratios, and also, I guess, you can also have information, you probably have information on absorption line stuff. So from your simulation, especially when you have different non-equilibrium processes, is there a reasonable spectral resolution, or signatures of these features might vary over different structures? Can you sort of educate us on at what spatial and spectral resolution that we should be observing these things to be able to infer about the physics?
So I don't have a good answer to that question. So I'll sort of like answer a slightly tangential question, if that's okay. And I think, you know, one of the things that, you know, we constantly talk about is like the CGM is multi-phase, right? And sort of when we see these absorption lines, we tend to find like sort of the high ionization states sort of like overlapping with the low ionization states. And that's really puzzling, right? Because is the gas somehow like well mixed and multi-phase, or are we seeing something else? And so that's one of the questions we're trying to address in these simulations. Now, I don't have an answer for what spatial and spectral resolution you need to sort of differentiate that and how much the non-equilibrium effects sort of affect that. But what I can say is sort of one of the things that maybe I shouldn't be surprised about that I saw is sort of this map of oxygen 6. Oxygen 6 is right here, and maybe people who've been studying this for many years already know this, but you can see it forms like layers around these filaments, and there's sort of like oxygen 4, oxygen 3, 2 sometimes embedded in it. And so it's possible that the gas is like not necessarily multi-phase and that it's not well mixed spatially, but what you're seeing is sort of like the highest density regions where you have these like layers of ionization. And these layers of ionization, this is where the non-equilibrium effects do happen, because that's where the gas is recombining. And so if you have a wave that goes right over it, then you have about a 30 million year time period where you're out of equilibrium. And so the question is are we biased to seeing it during that 30 mega year period or not? I don't know. But I think it's a really interesting thing to look into. And then we can, if we find that it is out of equilibrium, we can start talking about what sort of observational capabilities we need in order to differentiate these sorts of things.
Thank you. That's very, very helpful. I see Joe.
Yeah, really exciting stuff here, Harley. While you've got this slide up, I'm curious about something. So just to verify, the oxygen 6 that we see here is photoionized oxygen 6, correct?
Not necessarily. So the simulation includes photoionization, collisional ionization, things like that. So we haven't specified here whether it's photoionized or collisionally ionized, but that's something we can infer.
Okay, well, either way, you've sort of stopped in ionization level, at oxygen 6, but predominantly the hotter stuff is really going to be dominated by the oxygen 7 and oxygen 8. And so, is there this sort of hard threshold where if you were to show that on the plot, it would be this kind of isotropic, more homogeneous volume filling kind of medium? Or have you all looked at that?
Yeah, that's why I didn't show it, because it makes my plot look bad. So if I plot oxygen 7 here, you're right, it's much more volume filling. Like all the space in here is like oxygen 7, oxygen 8, right? So it's like it doesn't look as good, which is why I didn't show it. But indeed, the higher ionization states of oxygen are much more volume filling.
But just an important takeaway is that it looks very, very different than the oxygen 6.
That's right. It looks very different indeed. That's correct.
Thanks.
Crystal, is there a new question, or is this a hand up from before? Anyways, I have another
Sorry,
quick
it's from
question.
before.
Harley, we are out of time, but I'll quickly ask this question. You showed the time scales in a previous plot where you had equilibrium and then the non-equilibrium curves, and you said that the gas could be in any of these, and you had a time scale over there. So I just wanted to understand if this time scale has other dependencies, like maybe your structure, how big the cloud is and where it is with respect to the galaxy, or within, say, half of forever, within a million years, should we sort of, actually this is 10 million years, should we always expect things to come to equilibrium?
So I think, so this is sort of more just a demonstration of the non-equilibrium capabilities of the code. So I don't even remember how I set this up and what the conditions were, but yeah, you're right. In general, like this is subject to temperature. It's subject to gas density, electron density, things like this. It's subject to charge exchange as well. And so this time scale should not be taken as like a fiducial time scale. I think the 30 million years number is like a pretty good number to just have in the back of your mind. But as I said, that kind of like fluctuates by factors of 10 up and down. It can fluctuate by even more depending on the gas density. That's kind of the time that I think about. But the other time scale that really matters is how, and Ben Oppenheimer showed this with his sort of AGN paper, is how quickly the radiation field is also fluctuating. And so if the radiation field is like constantly fluctuating on shorter time scales than the sort of like 30 to 100 million years, you can kind of like keep the CGM out of equilibrium for much longer periods of time. So it's dependent on both, yeah, the radiation field fluctuating and the recombination time scale that matters.
Nice, thank you so much. Any last questions? We are out of time, so if not, let's thank our speaker once again. We are truly amazed by the work, and we look forward to seeing more results from you and your group. Thank you for joining us. And yeah, happy Halloween to everyone, and happy Diwali for those who are celebrating. And we will see you next time.
Thanks, Sanj. Thanks, Shawan.
Thanks.